In this video, we want to talk about the binomial theorem expansion and its applications. A binomial is the sum of two terms, say A plus B. So we want to start the topic by expanding A plus B in parentheses and raised to the power 0. We know from our algebra that any number raised to the power 0 is 1. So we can write this as A plus B raised to the power 0 is 1. Now, if we increase the exponent by 1, then we have A plus B with coefficients 1 for A, and B has also gotten the coefficient of 1. If we increase the exponent again to 2, this gives us A plus B times A plus B. And we can multiply this by taking A and multiplying it by the whole of A plus B as the second term here, and B. So we have A times A plus B plus B times A plus B. This gives us A squared plus AB plus BA plus B squared. So if we group the like terms, we know that from the commutative property of multiplication, AB is the same as BA. So we can add these two items here to get A squared plus 2AB plus B squared. So the expansion of A plus B all squared will give us this expression. Okay, so if we increase and say that A plus B to the third power, then what we are saying is that we can multiply A plus B squared times A plus B. In the same way, we can say A, substitute this term here. We have A squared plus 2AB plus B squared plus B times A squared plus 2AB plus B squared. On multiplying, we have A cubed plus 2A squared B plus A times B squared will give us AB squared. And here we have plus B times A squared will give us BA squared. B times 2AB will give us plus 2AB squared. And B times B squared will give us B plus B cubed. We can group the like terms and sum. This gives us A cubed. We have 2A squared B plus BA squared. And that will give us 3A squared B. We can also add AB squared plus 2AB squared, and that also gives us plus 3AB squared. And the last term is plus B cubed. So in a nutshell, we have A cubed plus 3A squared B plus 3AB squared plus B cubed. This is the expansion for A plus B to the power 3. If we look at the coefficients, we see that the coefficient of A cubed here is 1. The coefficient of A squared B is 3. And that of AB squared is also 3, with the coefficient of B cubed being 1 in this position. So let's keep an eye on the coefficients. Okay, without wasting time, I want to write the fourth and then the fifth exponents of A plus B. Yeah, so this is the expansion for A plus B in parentheses raised to the power 4. And we see that for the coefficient we have 1, 4, 6, 4, and 1. And that of A plus B to the power 5, we have 1, 5, 10, 10, 5, and 1. So one would wonder, how do we get these coefficients of the expansion? And it is very simple. I'm using the Pascal triangle to write the coefficients of the expansions. So the Pascal triangle is given as follows. We have 1 and 1 here. So we have 1, 1 plus 1 is 2, and we have 1. We have 1, 1 plus 2 is 3, 2 plus 1 is 3, and we have 1. We have 1, 1 plus 3 is 4, 3 plus 3 is 6. Note that I always write the sum in the middle. 3 plus 1 is 4, and I have 1. So ending is always, the ends are always 1. And I have here as 1. So 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And I have 1. So I repeat 1, have 6, 15, 20, 15, 6, and 1. We notice that the Pascal triangle is symmetric. It's very symmetric. So we say it is what? Symmetric. See that it is symmetric. We have 1, 2, and 1. 1, 3, and 3, 1. We have 1, 4. We have 4, 1 here. So this is the middle. And we have 1, 5. You see you have 5, 1. So this is how we generate or develop the Pascal triangle. We call it the Pascal triangle. And they give us the coefficients to the expansion of the binomial terms. But before we go on, I want to show some interesting features of the Pascal triangle. On the Pascal triangle, if we look here, we see that we have 1, we have 2, we have 3, 4, 5, 6, 7, 8, and it goes on. If you look at this, you see that 1 plus 2 is 3, and 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, and 15 plus 6 is 21, and 21 plus 7 is 28. Okay, now if we look here, we can see that we have this triangle are multiples of 3. You can see multiples of 3 here, and we can also see multiples of 3 there, multiples of 3 here. We can see multiples of 3 here. All these are multiples of 3. When we come here, we can see that these are multiples of 5. All these in the yellow triangle are multiples of 5. We can also get multiples of 2 in this. The Pascal triangle has so many interesting features, and they give the coefficients of the binomial expansion. So as we can see, the numbers in this triangle give us the coefficients of the binomial expansion. The first thing we did was to expand or have this to the power 0, and we saw that we got 1, and that is what is here. The second item was a plus b to the power 1. We got the coefficients to be 1 and 1 plus b. The third item was a plus b squared, and that gives us a squared plus 2ab plus b squared. The third, we got a plus b cubed, and that gave us a cubed plus 3a squared b plus 3ab squared plus b cubed. And that goes on and on. Let's take note that the coefficients are given by the values in the Pascal triangle. And okay, so we can do for the rest as follows. So this is how we generate or expand these binomial terms using the Pascal triangle. We take note that when we have a plus b to the power 3, a starts with the highest power of 3 and decreases to 2, decreases to 1, and then here a to the power 0. We see that b also starts here with a power of 0 and it increases to 1, 2, and then to the highest power 3. So in a plus b to the power 4, we also notice that a starts with the highest power of 4, and then it reduces to 3, to 2, to 1, and then 0. Likewise, b also starts from here. It is to the power 0 here. It increases. So whilst a is decreasing, b is increasing. And whilst a is increasing, b is decreasing. So that's how the binomial expansion works. Now, one other interesting thing that we can see about this Pascal triangle is also that if we look at this, we see that we have, if we sum what is here, we get here as 2, and this 1 plus 2 plus 1 is 4. This one also gives us 1 plus 3 is 4 plus 3 is 7 plus 1 is 8. This is 16. This is 32. This is 64. And we see that we have 2, 4, 8, 16, 32, 64. We can say that it is 2 raised to the power n, where n is 0, 1, 2, 3, 4 powers that we have on this binomial terms. Let's try to solve some problems of the binomial expansion using the Pascal triangle. So the first example that we'll take is 1 plus x to the power 5. If we have this, once we know that it is an exponent of 5 or a power of 5, then we know that the coefficients will be given by the numbers in this row. So we can write them down and say 1, and then we have plus 5 plus 10 plus another 10 plus 5 and plus 1. So this will be the coefficients that we have. And the terms are going to be that 1 will start with the highest exponent of 5 and x will be to the power 0. So here 1 will reduce to 4 and x will raise to 1. 1, 3, x, 2. Don't forget that the exponent should always add up to 5. So we have 2 and x, 3. And we have 1. For the sake of these examples, I'm writing the 1 because I know that it is always going to be 1. Well, no matter whatever number I raise it to. So 5. So this is going to give me 1 plus 5x plus 10x squared plus 10x3 plus 5x4 plus x5. So this will be the expansion for the 1 plus x exponent 5 or to the power 5. The next example will be 1 plus 2y to the power 4. So once it is raised to the power 4, then we know that the coefficients will be given by this row in the Pascal triangle. So we can write them down. 1 plus 4 plus 6 plus 4 plus 1. And as usual, this time I'm not going to write the 1 raised to the power 4. So I'll write 2y raised to the power 0, 2y raised to the power 1, 2y raised to the power 2, 2y raised to the power 3, and 2y raised to the power 4. On evaluating, we would get 1 plus 4 into 2y plus 6 into 4y squared plus 4 into 8y cubed plus 16y4. So 1 plus 8y plus 24y squared plus 32y cubed plus 16y4. This will be the expansion for 1 plus 2y to the power 4. So we are using the Pascal triangle to expand the binomial 1 plus 2y as we have seen. The next example would be, example 3 would be 2 plus 3y to the power 4. And this, because it is to the power 4, will still have the same coefficients. Plus 4, plus 6, plus 4, plus 1. Okay, because the Pascal triangle is symmetric, I want to write the polynomial in a descending order. So I can interchange the positions of 2 and 3 and write them as 3y raised to the power 4. So instead of starting it raising to the power 0, I'm starting it raised to the power 4 and 2 raised to the power 0. 3y raised to the power 3, 2, 1, and 3y raised to the power 2, 2 raised to the power 2. 3y raised to the power 1, 2 raised to the power 3, plus 3y to the power 0, 2 raised to the power 4. This now gives us 81y4 plus 4 times 27y3 times 2 plus 6 into 9y squared times 4 plus 4 times 3y and 8 plus 16. Final answer will then be given by 81y4 plus 4 times 2 is 8. 8 times 27 is 216y3 plus 6 times 4 is 24 times 9 is 216y squared plus 4 times 8 is 32 times 3 is 96y plus 16. So this will be the expansion for 2 plus 3y raised to the power 4. And as we can see, now we have the polynomial in a descending order of powers of y. We have y4, y3, y2, y1, and 0. Okay, so this is how we use the Pascal triangle to find the coefficients of the binomial expansion. What happens is that when the exponents or the powers of the binomial term are small, then we can apply the Pascal triangle to find the coefficients of the expansion. But when the powers or the exponent of the binomial term is high, say we have a plus b to the power 15, or say 1 plus 6y to the power 25. If we have something like this, and to be difficult to find the coefficients, so we're going to use a different approach to compute the coefficients. In our next lesson, we're going to introduce what we call factorial and combination to compute the coefficients of the binomial expansion.